In this lesson, I'm going to show you how to calculate the speed of a wave on a string. This question is based on the video which may be found at this address. So a wave is created on a string using a wave generator. The length of the string is 43 centimeters. One end of the string is connected to the generator, while the other end is connected to a 200-gram mass that provides tension in the string. Now we're told that a 6.4 meter length of this string has a mass of 8.05 grams. We will need that information to determine the linear mass density of the string. The generator creates a wave vibrating at its natural frequency. And we have two questions: to calculate the speed of the wave and to calculate the frequency of the generator. And then you'll compare that answer to what you see in the video. So let's begin by just sketching the wave. We're told that it's the fundamental frequency. Fundamental frequency has one antinode and a node on either end. That makes that the fundamental. Fundamental. And the fundamental would be the frequency 1, the first harmonic. So that is half the wave. And because it's half the wave, we know the wavelength is going to be twice what the length of this particular part of the string is. So lambda is going to be equal to 2 times, we're told that it's 43 centimeters. 43.0 centimeters, which is 86 centimeters, which converts to 0.86 meters. So remember that all measurements have to be in MKS, meters, kilograms, seconds. So we now have the wavelength. Now, we know that the speed of the wave may be determined by the formula Ft divided by the linear mass density, m divided by L, quantity square rooted. Now, the tension on this string is provided by this hanging mass. And in this case, we're told that this hanging mass is 200 grams. So that 200 grams, we're going to have to convert that to kilograms, because remember, MKS, meters, kilograms, seconds. So that's equal to 0.200 kilograms. Okay, so let's delve into this equation. What do we know so far? Well, we don't know any of these things, except we do know the mass and we do know the length. The mass of a long piece of string, 6.4 meters, and that length has that mass. So we can actually calculate m over L. But I need to figure out what Ft is. So Ft is provided by the suspended mass. So Ft is the tension that's being pulled on the string, forming the wave between those two nodes. And we know gravity is providing that tension. So we know that this is stationary. So Ft is equal to the weight. And the mass is 0.200 kilograms times 9.81 meters per second squared. And that's equal to 1.96 newtons. So that's what Ft is. Okay, so we're set. So I'm just going to place that in a box because it's a separate calculation. Okay, so now let's deal with this m over L. What is that? Well, for me to figure out what the mass is, I need to make a conversion because I'm told that we have 8.05 grams. So let's multiply that by 1 kilogram over 1,000 grams. That cancels, so that works out to 0.00805 kilograms. And that would be the mass of a piece of string, and we know our piece of string is equal to 6.4 meters. Okay, let me just point out that this problem deals with two lengths. It deals with the length of the wave, and in the case this is fundamental, so that length would be half of the total wave. The wavelength is 0.86, but the length of the fundamental is half of that amount, 0.43. But this business right here, the M over L, this is like any length of the same type of string. So we have to make that calculation separate. So let's figure out what the velocity is. Velocity is going to be equal to Ft over m divided by L, square root. Plug in the numbers. We have 1.96 divided by 0.00805 divided by 6.4. That's m over L. So let's further reduce that to 1.96 divided by, so this ratio here is going to be equal to 0.00126, and reduce that down, and we get square root of 1.556, which finally we get an answer of velocity is equal to 39.4 meters per second. And that's the answer to A. Now B is asking what's the frequency? Well, B, we'll do that over here. B, velocity is equal to lambda times frequency. So that means that frequency will be equal to velocity over lambda. So we just calculated the velocity. That's 39.4. And the lambda, we determined that earlier. That's 0.86. So the frequency is equal to 45.8 hertz. And if you look on the video again, you'll see that I dialed in a frequency of 46 to create the standing wave at its fundamental.